China's 621 miles per hour Maglev Train, the T-Flight. Introduction. China is advancing rapidly in the realm of transportation technology with its ambitious development of an ultra-high-speed Maglev train, the T-Flight, which aims to reach speeds of 621 miles per hour, 1,000 kilometers per hour. This next-generation train represents a significant leap in transportation, utilizing magnetic levitation technology within vacuum tubes to achieve unprecedented travel speeds. The T-Flight is positioned to drastically reduce travel times between major cities, such as cutting the journey from Beijing to Shanghai from roughly 4.5 to 6.5 hours down to a mere 90 minutes. Key developments and testing. Initial testing. The T-Flight underwent its first major testing in February 2024, where it achieved commendable speeds of 387 miles per hour, 623 kilometers per hour under low vacuum conditions. This was a crucial milestone that demonstrated the train's potential and its capability to meet performance parameters. Following this, further tests conducted in October 2023 confirmed its operational efficiency under non-vacuum conditions, solidifying confidence in the train's performance. Technological innovations. A significant aspect of the T-Flight's development is the integration of 5G technology, which is essential for maintaining stable communication and data transfer at near-sonic speeds. Researchers from Southeast University proposed an innovative solution involving the installation of parallel cables within the vacuum tubes. This setup allows for uninterrupted connectivity, ensuring that passengers can enjoy online services such as streaming and gaming while traveling at high speeds. This technology aims to address challenges related to signal disruption caused by the train's rapid movement. Future prospects. The next phase of testing for the T-Flight will focus on achieving its maximum speed of 621 miles per hour. This will require an extended track of approximately 37 miles, 60 kilometers, allowing the train to fully demonstrate its capabilities. There are ambitious plans for future phases that may target even higher speeds, with speculation about reaching up to 2,485 miles per hour, 4,000 kilometers per hour. However, these figures remain speculative and unverified. Common themes across sources. Speed and efficiency. Various reports consistently highlight the T-Flight's potential to surpass conventional air travel speeds, placing China at the forefront of high-speed transportation. The train's ability to connect major urban centers rapidly is a central focus, emphasizing the need for efficient travel solutions in a country with a vast population. Technological challenges. Challenges related to communication stability and safety at such high speeds have been recognized across the board. The innovative solutions being proposed by researchers, particularly the use of 5G technology and new cable systems, are seen as vital to overcoming these hurdles. Investment and infrastructure. China's substantial investments in high-speed rail over the past 15 years have equipped the country with the necessary expertise and infrastructure to support the development of the T-Flight. This historical commitment positions China uniquely in the global transportation landscape, enabling it to advance new technologies more rapidly. Differences in reporting. Focus on technological aspects. Some sources place a stronger emphasis on the technological innovations of the T-Flight, particularly the integration of 5G technology and the challenges of maintaining communication at high speeds. Others delve deeper into the practical testing results and the expected outcomes of the train, providing a more comprehensive overview of the project's progress. Outlook on viability. While some reports express optimism about the economic viability of the T-Flight project due to China's large population and existing infrastructure, others raise concerns about feasibility and potential safety issues associated with such an ambitious undertaking. The debate over the project's completion and its practical implications continues to be a focal point of discussion. Timeline of events. October 2023, successful tests of the T-Flight under non-vacuum conditions confirm its capabilities. February 2024, initial testing of the T-flight shows promising results achieving a speed of 387 miles per hour. Future testing planned. The second phase of testing aims to reach the maximum speed of 621 miles per hour, requiring extended tracks and further advancements in technology. Conclusion: China's ambitious plans for a 621 miles per hour maglev train, the T-flight, highlight the country's commitment to revolutionizing transportation technology. As the project progresses, it faces both challenges and opportunities that could define the future of high-speed rail travel. The integration of advanced technologies such as 5G and the existing infrastructure will play crucial roles in determining the success of this groundbreaking initiative. If successful, the T-flight could reshape travel dynamics within China and set new standards for transportation worldwide. China's ambitious development of the T-flight, an ultra-high-speed maglev train that could reach speeds of 621 miles per hour, 1,000 kilometers per hour, presents several counterintuitive aspects that challenge conventional expectations about transportation technology and its implications. 1. Speed versus safety concerns. One might intuitively think that the faster a train travels, the more dangerous it becomes. However, the T-flight's design incorporates advanced safety features that paradoxically make high-speed travel potentially safer than traditional rail systems. The maglev technology minimizes friction and mechanical wear, reducing the risk of derailment. Furthermore, the use of a vacuum tube significantly reduces air resistance, which can lead to more stable travel conditions compared to conventional trains. This raises the question: could the safest means of travel actually be the fastest? 2. Economic viability versus investment risks. It seems counterintuitive that a project with such immense costs and technical challenges could be seen as economically viable. Critics often highlight the exorbitant expenses associated with developing high-speed rail infrastructure. Yet China's vast population and rapid urbanization may provide a substantial market for this technology. The potential to drastically reduce travel time between major cities, such as cutting the Beijing-Shanghai journey to 90 minutes, could stimulate economic growth and justify the investments. This suggests that when viewed through the lens of long-term benefits, high-speed rail projects may be more economically viable than they initially appear. 3. Technological integration versus communication challenges. The integration of 5G technology into the T-flight system seems like a straightforward enhancement. But the challenges of maintaining stable communication at near-sonic speeds are profound. The intuitive assumption might be that faster speeds would complicate communication. However, researchers have developed innovative solutions such as laying parallel cables within the vacuum tubes to ensure continuous connectivity. This counterintuitive approach highlights how challenges associated with high-speed travel can lead to novel technological advancements that improve overall system performance. 4. Public perception versus technological acceptance. While one might expect public skepticism towards such radical transportation innovations, especially given Elon Musk's Hyperloop project abandonment, China's push for the T-flight demonstrates a contrasting narrative. The public's increasing acceptance of high-speed rail technology in China, fueled by past successes in the sector, suggests that innovative transportation solutions can gain traction even when they seem overly ambitious or futuristic. This reflects a broader trend where populations are more willing to embrace high-speed rail as a part of their daily lives, challenging the notion that people resist major changes in transportation. 5. Environmental impact versus infrastructure development. Typically, one would assume that constructing extensive high-speed rail systems would have a significant negative impact on the environment. However, the T-flight's design aims to operate within vacuum tubes, which could minimize land use and reduce the carbon footprint associated with traditional air travel. This counterintuitive perspective suggests that innovative transportation solutions may in fact pave the way for more sustainable travel options than previously thought possible. 6. Technological feasibility versus economic constraints. The ambitious goal of reaching speeds of up to 2,485 miles per hour, 4,000 kilometers per hour, is often dismissed as unrealistic. However, the very pursuit of such extreme goals can drive significant advancements in technology. The T-Flight's development may lead to breakthroughs that, while not immediately practical, could lay the groundwork for future innovations. This challenges the assumption that feasibility should be the primary driver of research and development, suggesting instead that aspirational targets can catalyze unforeseen progress. Conclusion: China's T-Flight represents a significant leap in transportation technology that simultaneously challenges and redefines conventional wisdom. By recognizing these counterintuitive aspects, we can better appreciate the potential of high-speed rail systems and their role in shaping the future of travel. The integration of advanced technologies, the economic implications of speed, and the quest for safety all intertwine in a narrative that positions the T-Flight not just as a train, but as a transformative force within the broader context of global transportation. China's development of the 621 miles per hour Maglev train known as the T-Flight represents a significant leap in transportation technology that merits close examination. While many reports highlight the impressive speed and potential efficiency of this train, there are several noteworthy aspects that may be overlooked by the general audience but are crucial for understanding its broader implications. 1. Technological integration and challenges. One of the most significant yet understated elements of the T-Flight project is the integration of 5G technology. As the train is designed to operate at near-sonic speeds, maintaining stable communication between the train and ground systems poses a complex challenge. The researchers from Southeast University have proposed innovative solutions, such as deploying parallel cables within the vacuum tube to facilitate uninterrupted connectivity. This technical aspect is significant because it not only addresses safety and efficiency concerns, but it also sets a precedent for future high-speed transport systems globally. The importance of this innovation goes beyond mere communication. It reflects a broader trend in transportation where high-speed systems must manage vast amounts of data in real time. The successful application of such technology could influence how future transport systems are designed, particularly in terms of safety protocols and operational efficiency. If China can demonstrate a reliable solution to this challenge, it could pave the way for similar systems around the world, fundamentally altering the landscape of high-speed travel. 2. Economic viability and investment. China's heavy investment in high-speed rail over the past 15 years has been a cornerstone of its strategy to lead in transportation technology. The T-Flight project is an extension of this commitment, but the scale of the investment required for such ambitious projects often goes unexamined. Critics have raised concerns about the feasibility and economic sustainability of the T-Flight, especially considering the high costs associated with constructing extensive vacuum tube networks. However, the potential economic benefits are substantial. By significantly reducing travel times between major cities, the T-Flight could enhance economic connectivity within China, fostering growth in various sectors including tourism, commerce, and regional development. While many reports focus on the technological marvel of the train itself, understanding the economic motivations and implications is essential. This project could not only redefine domestic travel but also position China as a leader in international transport technology, potentially exporting this model to other nations. 3. Safety and regulatory framework. Another critical aspect that often receives less attention is the safety concerns associated with operating a high-speed maglev train in a low-vacuum environment. The implications of a tube depressurization or other unforeseen incidents are profound. The safety protocols that will need to be developed and implemented are not just technical challenges but involve regulatory frameworks that require careful planning and international cooperation. The significant question of safety protocols is especially relevant given the ambitious target speeds of the T-Flight and the proposed future phases aiming for even higher velocities. The consequences of a failure at such speeds would be catastrophic. and thus the regulatory environment surrounding these innovations will be crucial. Understanding the safety measures and regulatory hurdles is essential for anyone looking to comprehend the viability of the T-flight and similar projects globally. 4. Environmental considerations. While the focus is often on speed and efficiency, the environmental impact of such projects warrants attention. The construction and operation of vacuum tube systems will present various environmental challenges, including land use, energy consumption, and potential disruptions to local ecosystems. Moreover, the sustainability of energy sources for powering these trains is critical. China's investment in renewable energy sources could align with the operational needs of the T-flight, allowing it to promote a greener transport solution. This aspect may be overlooked in discussions centered on speed and technology, but is increasingly relevant in a world grappling with climate change and environmental degradation. The T-flight could serve as a model for sustainable high-speed travel if integrated with environmentally friendly practices. 5. Global implications and competition. Finally, the geopolitical implications of China's advancements in high-speed rail technology cannot be ignored. The T-flight positions China not only as a leader in transportation technology but also as a significant player in the global transportation industry. As other nations, particularly in the West, struggle to innovate in the high-speed rail sector, China's progress could exacerbate global inequalities in transport infrastructure. The potential for technological exportation also raises questions about global standards in transportation safety and efficiency. If China successfully develops and commercializes the T-flight, it could set a benchmark that other countries might follow, potentially leading to a homogenization of transport technologies or conversely a competitive arms race in high-speed transport. Conclusion. While the T-flight Maglev train heralds a new era of transportation with its astonishing speed and innovative technology, it is essential to look beyond the surface. The integration of advanced communication technologies, the economic implications of its implementation, the necessity for robust safety regulations, the environmental impacts, and the global competitive landscape all play critical roles in shaping the future of high-speed travel. These aspects are not merely technical details, they are pivotal in understanding the broader significance of the T-flight project and its potential to redefine transportation in the 21st century. 1. Technological innovations and communication challenges. One of the most significant aspects of China's 621 miles per hour Maglev train, the T-flight, is its integration of advanced technologies, particularly 5G. As the train operates at near-sonic speeds within vacuum tubes, maintaining stable communication is crucial for passenger safety and service quality. Researchers from Southeast University have proposed innovative solutions to address the issues of signal disruption due to speed and the challenges of base station installation in a low-vacuum environment. This technological advancement not only enhances the operational efficiency of the T-flight but also sets a precedent for future high-speed rail systems globally. 2. Speed and efficiency revolution. The T-flight has the potential to drastically change travel dynamics in China by significantly reducing journey times between major cities. For instance, the travel time between Beijing and Shanghai could be cut to just 90 minutes, compared to the current 4.5 to 6.5 hours by conventional high-speed trains. This leap in speed and efficiency not only positions China as a leader in high-speed transportation but also challenges existing modes of travel, including air travel. The implications for urban planning, economics, and environmental impact are profound, highlighting the transformative potential of this technology. 3. Investment in infrastructure development. China's extensive investment in high-speed rail over the past 15 years has laid a strong foundation for the development of the T-flight. This prior experience equipped Chinese engineers and researchers with the expertise needed to tackle the challenges of vacuum tube technology. The government's commitment to funding such ambitious projects underscores a strategic vision to enhance national infrastructure and improve connectivity, which is essential for economic growth in an increasingly urbanized society. The economic viability of the T-flight is further bolstered by China's large population. which can sustain the operational costs and demand for such high-speed travel. For future prospects and feasibility concerns, while the T-Flight's ambitious speed targets, potentially reaching up to 2,485 miles per hour, 4,000 kilometers per hour, are thrilling, they also raise critical questions regarding feasibility and safety. Experts express skepticism about whether the necessary infrastructure and technology can be developed to support such high speeds sustainably. Issues related to safety protocols, emergency response in case of system failures, and the enormous financial investment required for long-distance vacuum tube systems are significant hurdles that must be addressed. The discussion surrounding these concerns is crucial for understanding not only the future of the T-Flight but also the broader implications for high-speed rail technology worldwide. Here are three famous historical cases that bear similarities to the ambitious development of China's 621 miles per hour Maglev train. 1. The Transcontinental Railroad 1863 to 1869. The construction of the Transcontinental Railroad in the United States marked a significant milestone in transportation history. It connected the eastern and western parts of the country, drastically reducing travel time across vast distances. The project faced numerous challenges, including terrain difficulties, labor shortages, and financial issues. However, it was ultimately completed with tremendous national investment and ingenuity. Just as China is investing heavily in its maglev technology, the U.S. government and private investors poured resources into the railroad, which transformed commerce and migration patterns in America. 2. The development of the Concorde 1960s-1976. The Concorde was a turbojet-powered supersonic passenger airliner that flew from the 1970s until 2003. It represented a significant leap in aviation technology, capable of cruising at speeds over 1,350 miles per hour, 2,180 kilometers per hour, which was more than twice the speed of sound. The Concorde faced numerous technical challenges such as fuel efficiency, noise regulations, and high operational costs akin to the technological hurdles China faces with the T-Flight speeds. Despite its eventual commercial success, the Concorde was ultimately limited by economic factors and regulatory challenges, showcasing the complexities involved in pioneering high-speed transportation. 3. The Hyperloop concept 2013-present. Proposed by Elon Musk in 2013, the Hyperloop is a conceptual mode of transportation that involves passenger pods traveling through low-pressure tubes at high speeds, potentially exceeding 600 miles per hour, 965 kilometers per hour. The idea faced skepticism and challenges related to technology, safety, and infrastructure investment. While Musk's initial enthusiasm has waned due to financial and technological obstacles, various companies and countries continue to explore the Hyperloop concept, similar to China's current efforts with the T-Flight. This modern pursuit of ultra-high-speed travel reflects the persistent interest in transforming transportation, paralleling historical innovations that have reshaped society. These cases illustrate the challenges and transformative potential inherent in groundbreaking transportation projects throughout history. Future outlook for China's 621 miles per hour Maglev train. China's ambitious project to develop a 621 miles per hour, 1,000 kilometers per hour Maglev train known as the T-Flight presents a revolutionary approach to transportation that could significantly alter travel dynamics between major cities. As the project progresses, several key factors will shape its future, including technological advancements, economic viability, infrastructure development, and regulatory challenges. Below are predictions and analyses regarding the future of this groundbreaking transportation system. Technological advancements. 1. Speed and efficiency gains. The T-Flight is expected to achieve speeds that surpass conventional air travel, enabling passengers to traverse long distances in mere minutes. If the current trajectory of development continues, the train may reach its target of 621 miles per hour in upcoming tests scheduled for the next few years. There is even speculation about future phases aiming for 2,485 miles per hour, 4,000 kilometers per hour, though this remains to be seen. 2. Communication technologies. Integrating 5G technology will be crucial for maintaining stable communication systems as the train reaches near sonic speeds. Continued research into parallel cabling systems within vacuum tubes will likely yield further innovations that enhance connectivity, enabling passengers to enjoy seamless internet access during their journeys. 3. Safety protocols. Ensuring passenger safety at high speeds is paramount. Future advancements in materials science and engineering will be necessary to develop safety measures capable of mitigating risks associated with rapid depressurization or other emergencies. Innovations in real-time monitoring systems and automated safety protocols will also play a crucial role. Economic viability. 1. Investment and funding. China has a proven track record of investing heavily in high-speed rail infrastructure. Given the country's vast population, the economic feasibility of the T-Flight project seems promising. If operational, this maglev system could reduce travel times, significantly promoting economic activity by facilitating faster movement of goods and people. 2. Cost-benefit analysis. While the initial development costs are expected to be substantial, the long-term benefits could outweigh these expenses. Analysts predict that the increased efficiency in transportation could lead to economic growth, tourism boosts, and reduced congestion in urban areas. 3. Global leadership in transportation. If successful, China's Maglev Train could position the country as a leader in advanced transportation technologies. This could foster international collaborations and technology exports, further enhancing China's influence in global transportation networks. Infrastructure development. 1. Expansion of maglev networks. Should the T-Flight prove successful, there is potential for a nationwide maglev network connecting multiple key cities across China. This may include routes linking megacities such as Beijing, Shanghai, Guangzhou, and Shenzhen, effectively reshaping urban dynamics and commuting patterns. 2. Integration with existing systems. Future developments will likely involve integrating the maglev system with existing transportation networks, including high-speed rail, subways, and airports. This holistic approach could create a seamless transit experience for passengers. 3. International collaborations. China may seek to collaborate with other countries interested in maglev technology, positioning itself as a hub for research and development in this field. Partnerships could lead to the establishment of international maglev routes, enhancing global connectivity. Regulatory and safety challenges. 1. Regulatory framework. As the T-Flight progresses, establishing a comprehensive regulatory framework will be essential. This framework must address safety standards, operational protocols, and environmental considerations related to the construction and operation of vacuum tube systems. 2. Public perception and acceptance. Gaining public trust and acceptance will be crucial for the project's success. Continuous engagement and transparency regarding safety measures, environmental impacts, and operational efficiency will be necessary to foster a positive public perception. 3. Addressing environmental concerns. The environmental impact of constructing extensive maglev infrastructure will need to be carefully evaluated. Future projects will likely incorporate sustainable practices to minimize ecological disruption, balancing technological advancement with environmental stewardship. Challenges ahead. 1. Technical feasibility. Achieving the projected speeds of 621 miles per hour and beyond will require overcoming significant technical challenges. Continuous investment in research and development will be necessary to address potential issues related to vacuum maintenance, propulsion systems, and structural integrity. 2. Financial viability. The project's high costs may present financial challenges. China will need to ensure that the investment yields adequate returns, possibly through passenger fares, freight transport, or government subsidies. 3. Global competition. While China leads in maglev technology, other countries are also exploring high-speed rail solutions. China must remain at the forefront of innovation to maintain its competitive advantage in the global transportation landscape. Conclusion. The future of China's 621 miles per hour maglev train appears promising, with significant advancements in technology, economic potential, and infrastructure development. However, challenges remain, particularly in safety regulation and public acceptance. As testing progresses and the project moves closer to realization, the T-flight could redefine transportation in China and potentially set new standards for high-speed travel worldwide. If successful, it may not only transform domestic transit but also pave the way for international advancements in maglev technology, establishing China as a global leader in transportation innovation.